Now, part D, optimality of algorithms. Another important concept, optimality. Okay, so D.1, minimum selection problem. So we learn another basic question type, selection problem type. Yeah. So let me describe the selection. Yeah, actually the minimum problem, everyone knows the minimum problem. Yeah, but actually it's a special case of the selection problem. So later we will study the general selection problem. Yeah. Here, our problem number 4, find the minimum of an array. How easy it is, find the minimum. Right? Everybody knows how to find the minimum. Given an array, tell me which element contains the minimum value of the whole array. Is it easy to solve this problem? Yes, very easy, straightforward, but there is a very important concept here, optimality concept. The solution is easy, but the concept is very important. So I want to talk about, I want to use this example, this question, to explain the optimality concept. Okay, all right, so let's solve this problem first. Then we have optimality discussion. Now, given an array, here the array, if we do not mention ordered or unordered, then we assume it is unordered. Because we do not mention. We do not mention, you can only assume it is unordered. Okay? You cannot assume it's ordered. Yeah. Otherwise, find the minimum is too easy, right? If the array is ordered, the first element is the minimum. Too easy, right? Yeah. So you cannot assume that. Okay. Yeah. Then, question. Find the index I such that A of I is the minimum of the array. Okay, the question. Yeah, very simple. And the solution also simple. Okay, but we need to do, some very abstract discussion. The discussion is quite abstract. Yeah. The problem type here, selection problem. Selection. Okay, yeah. So what is a selection problem? Here, let me give you the definition of selection problem. Find the kth smallest element. The k should be given at the beginning. Yeah. K is a fixed number. It is given at the beginning. So then you find the kth smallest element in a given array. When k equals 1, that's this minimum problem. K equals 1. When k equals n, that's the maximum of the array, right? When k equals 2, then you'll find the second smallest element in the array, and so on. Okay? Yeah. But there is also a special case, very important. When k equals floor function of n over 2, then this function, you find the median. Finding the median. Okay? That's another important selection problem, finding the median. Okay, yeah. So here I give you the reference in the textbook. Yeah, these two sections, 2.3 and 4.5. Yeah. All right. Work and analysis. Yeah. First, let's get a solution first. Yeah. So simple, yeah, but we need to go through the whole solution. Do initialization. When we start, we need a variable called a min. we use this variable to store the minimum value of the whole array. But at the beginning, we assign the first value, we assign the value of the first array element, A of 0, to this variable, main variable. Okay. Yeah, so that's the initialization step. Then, the general step, we need to update this variable when we go through all the elements in this array. So the general step, we compare main with the current element of the array, A of I. When we do comparison, we have these cases. The first, when main is greater than A of I, that means we should update this main value because we find a smaller array element, right? So we should replace this main variable, the value of this main variable by A of I. Okay, so we do a new assignment. Main equals A of I. Okay, yeah. Otherwise, if the main less than or equal to A of I, we do not update it. We do not need to update it, yeah, because we do not find a smaller array element, so we do not update it. Yeah. And we keep doing this iteration until we reach the end. Yeah. So otherwise case, we need to, for the otherwise case, then we need to move to the next iteration. Okay, until we compare with the last element, I equals n minus 1. That means we need to go through all the elements in the array. Not like our search algorithm, when we find a match, we get out of the loop immediately. Here, we do not. We have to go through all the elements from the beginning to the end. Then we can say, if our main variable contains the global minimum value, global, the whole array, global minimum value, okay? Yeah, so that's the solution. That's the solution, all right? Yeah. Yeah, so at the end, our function returns this main value. Yeah. Then we complete the solution. Okay, we complete the solution. Okay, yeah, it's simple. Yeah. But the question, next question. How many comparisons do we need to find the minimum? So given an array with n elements, how many comparisons? After you see the solution here, can you find the exact number of comparisons to find the minimum? It's a simple answer. Can any of you type that number? And I want to see if it's correct. Jeanette, type N. Jeanette, type N. Any Dakota also N. Any different number I want to see? Any different number other than N? Other than N, is there some reasonable choice different from N? Yeah, we need to look at all the elements. Yeah, here, let me give you a little more information. Here, number of comparisons, okay? We only count the number of comparisons, not assignments. You know assignments, right? For example, this first initialization, this is assignment, not comparison. This is not a comparison. Okay, so for the first array element, we didn't do comparison. We just assign a of 0 to our main variable. After that, we do not need to compare main with the a of 0. The next time we only need to compare main with a of 1 and so on. Now, Jeanette got the correct answer, n-1 comparisons. Yeah. But not assignments, right? Assignments, comparisons, they are two different operations. They are two different operations. Yeah. Here, we like to count the number of comparisons. Yeah. Because we feel the number of comparisons is a better measure than the number of assignments. Yeah. Although you can use number of assignments to measure its efficiency, but not as good as comparisons. Think about that. Yeah. Later, when I have a chance, I will explain why we use number comparisons is better than we use the number of assignments. Okay, yeah. So you can think about it. Yeah, but here, the correct answer, we want to get accurate, exact answer, not approximate. If approximate, your n is a good approximation, right? Only one difference. Yeah. But here, if we like to have exact number, then we need to use this n-1. Yeah. This exact number is important because remember our goal for this part D, we want to study optimality issue, right? Optimality, then this n-1, we can claim this is an optimal solution. If n, not n-1, if n, then you cannot claim it's optimal solution, right? Yeah. So for optimal solution, we like to use the exact number of comparisons. Yeah. So because we have second half of the story, if this solution is optimal or not. Okay. Yeah. So let me go to this optimality issue quickly before the break. Yeah, we have 5 minutes before the break. All right. Answer is n-1. Then the question, is it possible to further improve the algorithm? Yeah. Every time when we find an algorithm, we need to think about, is there any room for improvement? Yeah, because we want, in general, we want to have the best solution if the cost is not too high. Yeah. Yeah. Right? Yeah. If we can control the cost, because finding the best solution, you may need to pay a lot of cost. If the cost is too high, we may not like to pay that high cost. Okay? Yeah. Other than that, then, all right, yeah. If the cost of sorting is less than the number to be worth it, right? Unfortunately, the cost for the sorting is much higher. Much higher, yeah. The much higher here, I can give you, yeah. But your thinking is correct. Yeah, your thinking is correct. Yeah, right. Here I can give you the cost of sorting n log n. N log n. So that's the reasonable cost for the sorting. This is the cost of sorting. So definitely you don't want to pay this much cost, right? Yeah. All right. Later, when we learn sorting algorithms, we will find this number, this cost number, why it is n log n. Yeah. Okay, all right, yeah. Yeah, but good point. Yeah, good point. Yeah. All right, yeah. So when we answer this question, is it possible to further improve the algorithm? Usually we have two options. Okay. The first option, improve the algorithm. Yeah. So if the cost is not the issue, so we always try to improve the algorithm the best we can. Yeah. But it's impossible to improve the algorithm forever, right? You have to stop somewhere, right? Nobody can improve certain algorithm forever, right? Yeah. But how do you know at which point you should stop looking at the improvement? Enough is enough, right? You should stop looking for better algorithm. How do you know which point, right? So the second option, if you can convince people that this algorithm is already optimal, then you do not need to look at it anymore because it's already optimal. Your solution is already the best in the world. There is no reason for improvement. Think about that. Yeah. And this solution, this n-1 comparison, this solution, it is optimal. It is the best that people can do for this particular question. Nobody can do better than this one. Nobody can do better than n-1. That means nobody can use n-2 comparisons to find the minimum of an array with n elements. It is optimal. Okay? Yeah. So here, there is this issue. So this solution is optimal. But the question is, how do you know it's optimal? Right? You claim it is optimal, but you need to prove it. You need to convince people, right? Yeah. When you convince people, you need to give the convincing arguments. Otherwise, people won't be convinced. People won't be convinced. Okay? Yeah. All right. Let's take a 15-minute break. After the break at 7 o'clock, then let's look at the convincing arguments for this question. How to make the convincing arguments that this solution is already optimal. Okay? Oh. Let me explain the hard part. The solution is optimal. So that means for this particular question, finding the minimum of an array, you may have different solutions. Yeah, so let's consider all the possible solutions in the world. Okay, yeah. So among all the possible algorithms for this problem, how to show that this one is optimal? So this solution can beat, or no other solution can beat this one. No other solution can do better than this one. No other solution can use fewer than n-1 comparisons to find the solution. So that's what we want to show here. Okay? Is that hard? Yeah, think about it. Is that hard? Right? Yeah. So let's do that part. Yeah. Including unknown algorithms, right? All the possible algorithms, you need to include the algorithms that have not been developed, right? How do you know you can exhaust all the possible algorithms for this particular question, finding the minimum? Some algorithms may not have been developed at this point. Yeah. You also need to include those possible algorithms. The algorithm that could be developed in future, you also need to include those algorithms. So you can imagine how hard it is. Okay, yeah, you need to cover all those even unknown algorithms. You need to cover them. Think about, is that possible? Yeah. You will see it's possible. You know, we will show, you know, even those undeveloped algorithms in the future, you know, at this point undeveloped. In future, they will be developed. Even those algorithms we can cover. All right, in our discussion, we will cover them. Okay, all right. Yeah, here, yeah. Let me do the convincing argument. Yeah. Here, we need to use some imaginations based on our real world experience. Yeah. Yeah, because here, the optimality issue, it's an abstract, pretty abstract. Yeah, abstract means relatively hard to understand. Yeah. So in order to make the understanding easier, here I like to connect to some common real-world experience. Yeah. So if we connect to that experience, then the understanding will be much easier. Yeah. So what experience to connect? Our main operation is comparison. We compare two numbers. Which one is larger, which one is smaller? That's our basic operation. Yeah. But in the real world, we want to have some similar action to use corresponding to this comparison. Analogous to this comparison, some action in the real world. So what's that? Match sports, a match in a sports game. Match in a sports game. Yeah. Two players. So they need to play a game against each other, winner and a loser. That kind of activity, we use that activity as the comparison activity. Similar to comparison activity, we use sports match to understand the comparison operation. Yeah. All right. So a match between two players, the possible outcomes. Yeah. So when you do comparison, less than, yeah, because here, think about, in this question, we want to find the minimum. That means an element with smaller value, then it's better, right? A smaller element will be the winner, right? Yeah. When we compare two elements, the smaller one will be the winner. The larger one will be the loser, right? Yeah, here. So for that relationship, so when we have this less than relationship, we make the element that is less than the other one the winner. Okay, yeah. For the winner, that player gets a win. It gets a win. Yeah. Equal, then tie, greater than, lose, or loss. Okay. Yeah. So this kind of, analogy. All right. Yeah. Now, with this understanding, let me make the convincing argument. Yeah. All right. Imagine that Ming is the final winner. Yeah. So for a sports game, many players, fighting for the championship. Okay? Fighting for the championship. Yeah. And we want to find the final winner of the championship. Okay. Yeah. So that champion corresponds to the Ming value here in this question. Yeah. All right. The champion needs to beat all the other players, all the other elements in the array through comparisons, directly or indirectly. Here, this is important. Directly or indirectly. Yeah. This part slightly different from the real world situation. Yeah. All right. Directly, when we compare A and B, A less than B, we call this, B is a direct loser of A because there is a match, there is a game between these two players. Between these two players, A less than B, So it's a direct comparison. Okay? Indirect. All right, so indirect here, A less than B and B less than C, then we can say A less than C by transitivity, right? Transitivity property. Transitivity property. Okay? Transitivity property. In the real world, we cannot use this sometimes we may not be able to use this transitivity property, right? Yeah. But in math, we can always apply this transitivity property, right? In math. In real world, sometimes we can, sometimes we cannot, based on the rules. Yeah, based on the rules. Yeah. But here, in this particular question, we can apply this transitivity property. So that means we do not need to compare A with C directly, right? By the transitivity, we already know A less than C. Why we need to do another comparison? A with C. Yeah. If we have A less than B and a B less than C, it's enough. A less than C, right? Yeah. So in that situation, we call it indirectly. Okay. A beats C indirectly. Okay. Yeah. So, all right. Now, next, if an element loses once, then it is eliminated. Yeah. If an element loses once, it cannot be the minimum, right? If it loses once, that means it's greater than one element, at least one element. Then it cannot be the minimum. If it is not the minimum, then we can eliminate it from the minimum consideration, right? Yeah. So we have this statement. If an element loses once, it is eliminated. Okay, all right, yeah. Then next statement. Each comparison can only eliminate one element. Yeah, because each comparison, you have one winner, one loser. That loser is eliminated. cannot eliminate more than one element, right? After one comparison, you eliminate two elements. That's impossible. Yeah. So each comparison can only eliminate at the most one element. Yeah. How about that? If we say at the most one, yeah, because you may do some redundant comparison. If you do redundant comparison, you may not be able to eliminate anyone, okay? Because you do some unnecessary comparison, okay? Yeah. So here, to say better, more accurate, yeah, can only eliminate at the most one. At the most one. Yeah, because there is a possibility you do some redundant comparison. No element, no new element is eliminated. Yeah. Yeah. All right. Yeah. Next one. We need to eliminate n-1 elements in order to find the minimum. Yeah. Think about it. To get a final winner, you have to eliminate all the other elements, all the other players. Only the final winner, the champion, remains. All the other players must be eliminated. n-1 players, or here, n-1 elements must be eliminated in order to determine the final winner minimum. Thus, we need at least n-1 comparisons. Yeah, because one comparison you can only eliminate at the most one. In order to eliminate n-1 elements, you have to do at least n-1 comparisons. Think about that, this argument. Yeah, this is the critical one. So this argument is the critical one, okay? Yeah. No matter which way you do, in order to find the minimum, you have to eliminate n-1 elements. To get that, you need to do at least n-1 comparisons. You may use more than n-1 because you may do redundant comparisons. If you do redundant comparison, you use more than n-1 comparisons, but the minimum is n-1 comparisons. That means you cannot use n-2 comparisons to find the minimum. Because n-2 comparisons, you cannot eliminate n-1 elements. Right? Yeah. n-2 comparisons has no way to eliminate n-1 elements. Okay? Yeah. So then we can say, after all these statements, we can say the best solution is n-1, and our current solution is the best because our current solution has this exact n-1 comparison. How about this? Okay, yeah. Yeah, we try very hard, you can see, yeah. But after this sequence of statements, then we show people this solution is really the optimal solution. Nobody in the future, in our future generations, can do better than this one. Okay? Yeah. Yeah. You know, yeah. So that's the final conclusion. Yeah. Final conclusion. So this solution is optimal. Okay? Yeah. Yeah. And This question, yeah, this question is simple. Finding the minimum. This question is simple. Yeah. And then later we will have many different challenging questions will be based on this one. Yeah. So I hope you spend some time to study this question better. Yeah. Because later, yeah, when I assign you homework questions, yeah, some of the several questions will be based on this one. Yeah. Several challenging questions will be based on this one, the simple one. Yeah. But if you do not understand this question well, then it will be very hard to solve those challenging questions. Okay, yeah. Yeah. All right, so we complete whole module 1, part D, A, B, C, D, yeah, the whole module, module 8, module 1, yeah. Okay, all right. Yeah, any question at this point? Yeah. 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 All right, so if no question, I want to move to the programming project, polynomial evaluation. Yeah. So I want to talk about, oh, all right, yeah, before that, yeah, here we use the elimination method, yeah, yeah, because here we talk about eliminate certain number of elements, yeah. So I want to emphasize this elimination idea is very important, yeah. Later, we will have many questions. If you use this elimination idea, then it will be much easier. Yeah. People may not be aware of this elimination approach, idea, thinking. Yeah. Then it could be very hard. Yeah. So here I emphasize, yeah, so let's, do a summary, this elimination method. The first time we use this method here, elimination method. Yeah. All right, so what's that? This elimination method. Try to eliminate as many as possible elements. Yeah. Because when you do analysis, after some comparisons, here we mainly, we use the comparisons. After a certain number of comparisons, we notice that some of the elements cannot be the candidates, candidates for some goal. Here, our minimum is the goal, right? Yeah. Some of the elements after a certain number of comparisons, they cannot be the minimum. Cannot be the candidates. Yeah. Here I use this general word, candidate, because for different question, our candidate could be the different element. For example, our candidate could be the maximum, right? Yeah. If we change the goal, finding the maximum, then our candidate will be the maximum. Okay. If we change the goal to median, finding the median, then our candidate will be the median, and so on. Okay, yeah. So here, after a certain number of comparisons, if we get enough information to say that certain elements cannot be the candidate or candidates sometimes, yeah, we can eliminate them from the consideration. Right? Eliminate as many as possible. Because after the elimination, our data is reduced, the data size is reduced. Then the problem becomes easier. Yeah. That's the essence of this minimum. That's the essence of this elimination method. Okay, yeah. Here you may feel it's quite trivial, right? No. It's normal, it's trivial. Yeah. Later you will see you may not be aware of it. It is simple, it is natural, it is, you can say trivial, but many times you may not be aware of, oh, these elements can be eliminated. Later, when I point out, oh, these elements can be eliminated from the consideration, then, well, you realize, oh, I should eliminate them earlier. Yeah, earlier. Yeah. Later, you will have that situation. When we find the median later, I will give you questions, finding the median questions. Now, those questions usually pretty hard. Then you will have had the situation. Okay? Yeah. All right. Yeah. Question. Lacking understanding process, procedure for solving given problem. Problem type, how we are supposed to solve. All right, good. Yeah, Dakota, you're asking a very general question. Yeah, I want to say, in this class, I will teach you the general procedure to get there. Yeah. Remember, we need to apply many strategies, many techniques, many thinking methods, many principles. Okay? After you understand all those things, yeah, actually, in this whole class, I will, provide you typical ways to find solutions. Yeah. So many strategies. Remember, at this point, we have learned several strategies. Okay? Yeah. Start from simplest cases. That's one strategy, right? Yeah, think about. Okay? Principle, balancing principle, right? Yeah. Elimination method, right? So think about all these things. When you learn enough, if you can put them together, then you can do better and better in problem solving. Okay? Yeah, yeah. At this point, it's still early. You haven't learned much. Yeah, yeah. But you have already learned some of the effective methods. Okay? Effective methods, some of them. Okay? Yeah. And also, last time we also learned some greedy algorithm, right? Greedy thinking, greedy approach, so many different methods, techniques. Okay, yeah. All right, yeah.